Hey YouTube, welcome back to a brand new episode, and today we'll be expanding on our IK algorithm that we started in the last episode. Before I begin, I'd really appreciate it if you left a like and subscribed, because I really do put a lot of effort into these videos. If you guys didn't see the last episode, make sure to check it out, it will be in the description. You'll have to watch that episode in order to fully understand what I'm doing in this one. So last time we created the base algorithm, and in this episode we'll be adding extremely simple constraints to our joints. Then we'll be adding some code to create a bit of dynamic movement and make the movement more realistic. I just want to touch base on what's coming up very soon. So in this algorithm, the constraint system is actually created through an irregular cone being casted in a direction. This is a very complex process, and even I haven't fully gotten the hang of it yet. So once I do, I'll show you guys how to implement a complicated IK constraint system. But for now, this should be more than enough. If any of you figure out a solution for this IK constraint system, make sure to leave it down below in the comments and you could teach me a thing or two. But in the next episode, we'll be using IK and attaching it to an actual arm model. Then we'll create some third-person aiming controls with the camera and be able to move a gun to aim at a location with our mouse and make the IK snap onto the gun. So obviously we're all going to be learning a lot and having heaps of fun along the way. If you haven't already, make sure to smash that subscribe button to keep up with this awesomely original content, and without any further ado, let's get right into the video. So we have three things that we need to do today. First, we have to create the spherical constraint system, and then we have to create a little centroid movement system to create the dynamic movement, and then we need to change the ARM IK script to implement both of those new features. Okay, so all of these things are going to require previous knowledge from the explanation that I did in my last video. So if you haven't seen that, make sure you see that, and that will help you guys a lot. So first, what we're going to be doing is creating our spherical constraint system. So basically what this is just a little sphere that we clamp to a point, and then our joints can't move out of that sphere. It's a very simple constraint system, but it's extremely effective as far as I've used it. Okay, so I'm going to go in and start creating that right now. So I'm going to put these scripts on the upper left and upper right joints, because from the last episode, if I just play this and I show you, we have this little constraint, right? And when I move this, we can see our upper arm moves 360 degrees, okay? We do not want this type of movement, okay? It looks very unrealistic, as you guys realize, and we can't specify the direction that we want our arm to bend in, which is really, really bad. Okay, so let's go into our upper right and create a new script called spherical constraint, okay? And I'm gonna go in and let's begin coding our spherical constraint system. Before we do that, I'm gonna add the spherical constraint system to the upper left as well. Okay, now let's begin coding. I'm just gonna zoom in so you guys can see the text, our code, okay, and I'm gonna begin. So the first variable that we will need is a public float called sphere radius, okay? This will just define how big our sphere is. And then we need a public transform called relative object. Okay, so like I explained in my last video, the sphere will not be clamped to the object that it is working on, right? So you don't want the sphere to be relative to its own effector, because when this moves, the sphere will also move. That means that this joint will never actually leave the sphere, so it will never actually get clamped. So we need to make sure that the sphere is clamped onto another object, okay, which has a little bit less movement, which in this case will be the centroid object, okay. Now we need to define a vector3 offset to make sure that the sphere is coming away from the centroid in the direction of the actual joint that we're trying to constrain. Okay, I'm going to create a little private variable called center point, which will keep track of where our actual sphere is. So I'm just going to create a little private void update, and this is going to be the only update in the entire script. Okay, so we're just going to say relative object transform point, and we'll say offset. So if you guys don't know what transform point is, it basically takes a like a local coordinate, right, and turns it into world space. Okay, so if we give the local coordinates x1, okay, it will put a point over here, and then we can convert that point to world space, and it might give you x negative 5, okay? If you really want to learn more about that, you can just go over to the Unity documentation. They have a very good explanation of all of these functions. Okay, now let's go on to our gizmo, because as you guys know, I love adding my gizmo. I'm a very visual learner, and I love to see what I'm actually doing. Okay, so I'm just going to create a vector3c, and it's just going to be the exact same code as the previous line. Okay, now we're just going to say gizmo.color equals color.blue, and you can change the color to match your needs. Okay, so gizmo.draw wire sphere. We don't want to draw a sphere because then you won't be able to see the joint, and that kind of it doesn't look good. And the center point we're going to pass in C, and then for the radius we're going to pass in our sphere radius. Okay, so if we go in now, I'll explain to you how this sphere system is going to work. Okay, so our relative object is going to be our centroid. So let's attach our centroid, and on our upper right, let's attach our centroid as well. Let's increase the sphere radius to around 0.1, and we can see already there's a little sphere there. I'll just move that right now. So for our upper left, we will want to move our x in the negative direction, and it turns the local space, which is our -5 and all of that, into world space coordinates. So let's just position this at -5 because we know our joint is at -5, and for upper right, let's position it at 5. So now we have our little spheres. So this sides will provide a very limited amount of movement, right? And that's what we want. We don't want our shoulders to move too much. As you can see, when you roll your shoulders, you don't have too much movement on your shoulders, right? So that's what we're trying to simulate here, basically. And what we're going to do is we're going to go onto the centroid, and we're also going to create a spherical constraint over there. And for the relative object for the centroid, we're going to attach it to the capsule. Okay, so let's just increase the radius here. And we're going to make it really small, actually, because we don't want too much movement, okay? We want a little bit of dynamic movement to create that realism, but too much just becomes unrealistic after a point, okay? So let's create 0.1, 0.15 should be good, right? And let's drag it up until it's near the centroid, okay? Now, we have 3 spherical constraints. So, the spherical constraint for the centroid is clamped to the capsule, so it'll always stay in the middle. So, the centroid can't move out of that position, okay? Because when we're calculating our average for our root movement, like I explained in the last video, the centroid can go way off the center, and we need to constrain that as well. So, we'll just do it through this mean, okay? Now, let's go in and actually write our constraint script. Okay, so we need 3 functions for this. Just one to check if a point is in the sphere, and another function to clamp any point to the bounds of the sphere, okay? Because if the point is not in the sphere, then we want to clamp it into the sphere, okay? That's the basic logic behind this whole constraint system. And like I said, you can write any constraint system you want, okay? So it can be a box constraint, a cone constraint, it can be anything, and FABRIK will work with it and suit the situation or suit the constraint, okay? So let me create a public bool called point is in sphere, okay? Vector3 point. And we're going to pass in a point, and then we're going to return true if it is in the sphere, and return false if it's not, okay? So we're just going to get vector3 original point is equal to center point, and float radius is equal to our sphere radius. Okay, now we have these 2 little variables. We can say vector3 vecdist is equal to original point minus point. Okay, so now we're just getting the difference between the 2 points. Okay, very easy stuff. Now we're just going to get the distance squared. Okay, so this is very basic geometry, and it should be quite familiar to you guys. We're just going to get the dot product of the vecdist and our vecdist. Okay, and that should return if the f disk square is lower than the radius squared, then we can be sure that the point is inside the sphere. So if f disk squared is lower than radius times radius, then we can return true, because the distance between the point and the center point is lower than radius squared, which means the point is inside the sphere. Okay, and if it's not, then we can just return false. Very easy stuff right there. And now we're going to create our vector3 function, which will return a vector3 for the closest point on the bounds of our sphere. Okay, so let's do this now. Public vector3 closest point on bounds, and we're going to pass in a point. Okay, so let's see, vector3 original center is equal to center point. Vector3 is, float radius is equal to sphere radius. Okay, and float r equals what am I doing? Mistake there. Vector3 difference, we're gonna get the difference again. So point minus original center. Okay, and vector3 return point is equal to center point plus radius divided by the difference dot magnitude times difference times times 1f. Okay, we can change the 1f later if we need to. Okay, so basically what we're doing is we're getting the center point, adding the radius to get like the edge of the sphere, and then we're going to divide it by the magnitude to make sure it's inside the sphere. Okay, I think that's right, and then we can return the return point. Okay, now we have two functions that will help us in every way that we need. Okay, so now what we're gonna do is say public vector3 clamp if needed. Okay, so vector3 point. And all we're going to do now is we're going to pass in a point every frame for the upper joint and the centroid, right? And if the point is in the sphere, then we'll just return the same point because we don't need to clamp it, okay? But if it's not, we'll clamp it and return the new point, okay? So it's a very simple function. So if point is in sphere, point, okay, we're going to return point. Else, then we're going to return closest point on bounds, which is the point, okay? And since this returns a vector3, we can just return this method all by itself. So if the point is in the sphere, we return the point that we passed in. We don't need to change it. If it's not, then we return a clamped point on the edge of the sphere. That should be it for a spherical constraint system. Okay, now let's add our constraint to our arm IK. So let's go into our arm IK, and let's go to the very bottom. Here, what we're going to actually know, before we do that, we need to reference our spherical constraint. Okay, so let's go up and let's add a new header. Okay, and let's call this spherical constraints. I'm just going to full screen this. Spherical constraints. I'm going to add a public spherical constraint, and we're going to call this upper constraint. Okay, and we're going to go down, all the way down, and we're going to say if upper constraint is not equal to null, then we are going to do this entire little block of code. Okay, so the block of code is going to be temp upper. Okay, remember our upper ref, lower ref, and hand ref are actual cubes. Okay, the temp upper and temp lower and temp hand are our algorithm. Basically our temporary variables that we're storing, okay, and then we change the actual real game objects to fit those locations, okay, so we can still modify these temporary variables. So we're going to say temp upper equals upper constraint dot clamp if needed, and we're just going to pass in temp upper. So if temp upper goes past the constraint, then it will be constrained, okay, very easy stuff. But the problem with this is that the temp lower and all of that has already been calculated. So if you constrain the temp upper, then the temp lower and temp hand will continue to move and it won't preserve distance, which we already talked about, that preserving distance is one of the most important things that an IK algorithm has to do. Okay? So how do we preserve distance after we change where the upper arm is? Okay, all we have to do is temp lower is equal to temp upper. So I'll explain this logic in just a second. Okay, so you should kind of get an idea what I'm doing here before I explain it, but I'll just show you. So once we constrain the temp upper, right, temp upper has been changed. Okay, so all we have to do now is find the direction between temp upper, temp lower, no matter where temp upper is now, and normalize that direction and multiply by upper to lower distance. Okay, so if we normalize it, it doesn't matter how far away it is, the normalized vector will always be the same, and then we just multiply it by our original distance between the joints, and it should move the temp lower to fit our upper arm joint now. Okay, and now we're going to make sure that the lower hand, the hand is also preserving distance to the lower joint. Okay, so we're going to use the same logic here and just say temp lower plus temp hand minus temp lower. So we're getting the direction between temp hand and temp lower. We're going to normalize that and times by lower to hand distance. So we're preserving distance between these three joints. Now let's check it out. Okay, so let's go into our RE and LE. And before we actually begin, I just want to change something. Can we just get the right elbow and the left elbow, and let's just take it out of the effectors. I don't know why I put it there, my mistake guys, so let's just take it out and drag it onto the capsule, because the left elbow and right elbow are independent, okay? They need us to be controlled, we need to control them to suit whatever we want, okay? So in the RE, let's drag in our upper right, and it should automatically bring in the spherical constraint, and then in the LE, let's drag in the upper left constraint. Okay, now we have both our constraints, and let's check this out now. Okay, as we can see, if I go up and then I move this, we can see our upper arm joint isn't moving, and we're actually getting a bit of free range movement. Okay, so if I move back, we can see that the upper arm is moving back. Okay, so but we're not getting that crazy movement or the 360 way. Okay, now we're having a natural movement. Okay, same with this. Sorry, I'm moving the arms the wrong way, but we can see that we're getting very natural movement now, right? We can move it, and we just need to reposition our elbows to make sure our elbows are facing in the right direction, and we can see that our arms are getting constrained. We could stop here, but we never stop at the simple stuff. That's just boring. Let's go into the dynamic centroid movement. Okay, so in order to accommodate for this, we need to go into our arm IK, and we're just going to comment out this whole late update, because from now the root IK script will control both our arm IK updates. Okay, so all we're gonna go do is go into Unity, and let's click on our centroid. Okay, and now let's add a root IK script. Let's open this up. And before we begin, I would just like to organize those folders. Let me just go back into Unity. It's very not neat, and I don't like it. So let's just go in and drag this into our IK scripts. Okay, now we have a nice organized folder just for our IK. Okay, so let's go into our root IK script. Okay guys, we're gonna begin writing our root IK system. So I'm gonna say public arm IK, arm1. We're gonna reference both arms first, because this script is going to be controlling both arms. Okay, now we're gonna call our spherical constraint. Okay, spherical constraint, and we're gonna call this a constraint. And it has a red underline. I'm not sure why, but there are no errors in Unity, so it will be absolutely fine. Don't worry about that. Okay, so we're just gonna create a private void called late update, and we're going to create another private void called solve IK. Okay, and in late update, we're just gonna call solve IK, and solve IK is basically gonna run both of our arms. Okay, and if you guys remember in the last episode, in solve backward, we actually return our temp centroid, because when we solve backwards, we get a new centroid position. Okay, our new centroid position, yeah, and both arms will have slightly different centroid positions based on their new end effector. Okay, and all we're gonna do is get both of those temp centroids, divide them in two, which will get us the average of both new centroids, and set that as the original centroid for both of them, and that should create a nice realistic dynamic movement. So I'm going to go ahead and do that right now. Vector3 arm1v, which is arm1.solve backward, and we're just going to pass in arm1's end effector dot position. Okay, and we're going to say vector3 arm2v, and what we're doing here is just gathering our data of where both of our new centroid positions are. Okay, so we're just gonna do those two functions and that should solve backward. Now we're gonna find the centroid, and the centroid is just equal to arm 1v plus arm 2v divided by 2. Okay, and if we don't need to do if anymore, all we have to do is centroid is equal to constraint dot clamp if needed centroid. So what we're doing is we're finding a new centroid position. If that's out of our constraint range, then we'll clamp it back in, okay, to make sure that our centroid isn't moving all over the place. Okay, now all we have to say is arm1 dot solve forward from the centroid. Okay, and we gave the option to solve forward from a parameter, and we're going to pass in centroid, so both will have a new solving forward point. Okay, so one arm will affect the other arm will affect the other. Okay, that's what's so amazing about all of this. So we're going to say arm1.set temp pos, arm2.set temp pos, and both of them will have their position set now. And the last thing that we need to do is set the transform.position to equal the centroid, because this object is the centroid, and we need to move that, okay, in order to be where the centroid is, so both arms can affect each other in the proper way. Okay, so that should be it. And all we have to do is go into the centroid now, attach our parameters, and everything should work perfectly. So let's just put in RE as our arm1, LE as our arm2, and our constraint will just be the constraint on our centroid. And when we play, let's check this out. Let's go into scene, go into upper view, and let's try drag it. As you can see, one arm affects the other. We want to reach a bit further, we just pull forward, and one arm affects the other. So if I want to go a bit further this way, we can see that we are getting moved that way. If I want to go a bit further this way, we can see that we're getting moved this way. Okay, I just want to go in to RE, and we can see that we can increase our elbow effector position. I'm just going to do that just to create the proper movement, and we can see that we have very, very nice, rigid, and smooth IK now. Okay, so what we'll be doing in the next episode is basically placing these effectors onto a gun, right? And when we do that, all we can do is we can make the arms move to fit the gun position. Okay, I'm just gonna get rid of this elbow power to show you what I'm talking about. Okay, so what we'll do is we'll bend the right arm and the left arm in order to hold a gun. As you can see, we can just bring the arms together, right? And we're going to attach an actual arm mesh onto these joints and be able to rotate the joints to fit the lines of the actual arm, okay? And then we'll hold a gun and we'll write some camera scripts to rotate around the player, create an aiming function, shooting, recoil. Everything is going to be done in the next 2 episodes, and we're going to be learning so much. It's going to be so great, okay? So make sure you subscribe to keep up with that, and thank you guys for watching, and I'll see you next time.